Welcome, everyone. Thank you for joining this session. Today, we are going to explore From Stateful to Secure, a production journey with RabbitMQ on Kubernetes. This presentation serves as a comprehensive blueprint for deploying, exposing, and fortifying complex applications specifically on Azure Kubernetes Service, or AKS. We will walk through the critical stages of managing stateful workloads and transitioning them into a robust, secure production environment. Let's get started. Our journey to build and operate a production-grade RabbitMQ cluster on Kubernetes is a progressive path defined by 4 stages of engineering maturity. We will walk through this roadmap, starting from the initial foundation for data persistence and moving through to the final stage of zero-trust fortification. In Stage 1, Foundation, Understanding Persistence, we focus on the bedrock of our system. Here, we address the critical requirements for data durability and storage configuration, ensuring that our message data remains safe and recoverable. The second stage, Architecture, Reliable Deployment, is where we design the blueprint for stability. This phase involves configuring our cluster for high availability and resilience, ensuring that our deployment can handle real-world production demands. Once we have a stable architecture, we move to Stage 3, Accessibility, Secure Exposure. In this phase, we define how to safely expose our services to the outside world, implementing secure networking strategies that balance connectivity with strict access control. The final stage is Fortification, Zero Trust Security. This is the pinnacle of our journey, where we apply advanced security principles to verify every interaction within the cluster, creating a robust and fully defended production environment. The fundamental challenge in modern infrastructure is that while stateless applications are easy to manage, stateful ones are inherently difficult. To understand why, we can compare 3 distinct architectural patterns across key operational metrics. First, consider a stateless application, such as an Nginx web server. In this model, pods are entirely disposable because data is stored externally. This architecture allows for effortless scaling and near-instant failover. Because the pods lack unique identities or local data dependencies, the YAML configuration remains simple and low complexity. When we move to basic statefulness, like running SQLite with a persistent volume claim, or PVC, we encounter significant hurdles. Here, a pod is tied to a specific disk. This creates a data lock that makes horizontal scaling difficult or even impossible. Failover is slow because the system must orchestrate the detachment and reattachment of storage volumes. As a result, the management complexity of your configuration increases to a medium level. The most advanced approach is intelligent statefulness using an operator, commonly seen with complex systems like RabbitMQ. An operator acts as a software robot that manages the cluster's entire lifecycle. It automates scaling and handles failover intelligently by performing tasks like promoting a new primary node. While the internal logic is sophisticated, the operator hides this complexity from the user, keeping the YAML requirements low. Ultimately, simple statefulness only ensures that your data is saved, whereas intelligent statefulness manages the health and life cycle of the entire application. The operator pattern essentially acts as your automated site reliability engineer. At its core, an operator is a custom controller that extends the native capabilities of Kubernetes. Instead of managing complex infrastructure manually, you simply declare your desired state within a custom resource, or CR. The operator then takes over to handle all the intricate, application-specific logic required to reach and maintain that state. Looking at the workflow on the right, when you submit a request, for instance, a RabbitMQ cluster YAML file, the operator bot begins managing a suite of underlying Kubernetes resources. It automates several critical tasks that would otherwise be repetitive and error-prone. First, it creates a stateful set to ensure stable pod identities, which is crucial for applications like databases or message brokers, where identities must remain consistent. Second, it automatically provisions a separate persistent volume claim, or PVC, for every individual pod to ensure data persistence. Furthermore, the operator is responsible for injecting the necessary configurations to handle inter-node clustering, ensuring that the application components can communicate and synchronize effectively. Beyond these initial setup tasks, it provides advanced self-healing capabilities that go far beyond standard Kubernetes features. By managing services, secrets, and stateful components in concert, the operator pattern allows you to package operational knowledge directly into software, making complex distributed systems significantly easier to manage at scale. Let's examine the fundamental shift in how we manage stateful applications in Kubernetes, moving from the how to the what. On the left, we see manual statefulness. This imperative approach requires us to manage every detail. First, we must explicitly request storage by defining a persistent volume claim. Next, we have to force a recreate update strategy to avoid disk conflicts. And finally, we must manually mount that volume within the pod specification. On the right, we see the power of the operator pattern. Here, we define our desired state using a custom resource, such as a RabbitMQ cluster. The operator hides all the underlying complex stateful set logic. Instead of managing low-level resources, we simply specify our high-level needs, like the number of replicas and the required storage capacity. The operator then automatically creates the necessary PVCs and handles the orchestration. Ultimately, the operator pattern allows us to move away from tedious imperative configuration and focus entirely on declarative intent. Architecting for reliability often requires managing complex dependencies between operators and the applications they manage. The wrapper chart pattern, also known as the umbrella chart, streamlines this process by packaging the operator and the application into a single, atomic, and version-controlled unit. Instead of executing multiple separate commands to first install the operator and then the specific application instance, a single Helm install command triggers the deployment of the entire stack. As shown in this diagram, the wrapper chart includes the RabbitMQ operator as a dependency, which handles the installation of required custom resource definitions and the operator pod. Simultaneously, the chart contains a template for the RabbitMQ-instance.yaml file to create the RabbitMQ cluster custom resource. This consolidated approach ensures that all components necessary for a fully deployed RabbitMQ cluster are synchronized, making the deployment process more predictable and easier to manage. To understand the anatomy of a wrapper chart, we examine 3 essential files that work together to deploy complex applications. First, chart.yaml acts as the glue. This file is where we define our dependencies. By listing the RabbitMQ cluster operator here, we inform Helm that this operator, along with its custom resource definitions, must be installed first for the rest of the chart to function correctly. Second is values.yaml, known as the controls. This is a single, unified file used to configure both the operator subchart and your specific RabbitMQ instance. It allows you to manage settings for the entire deployment, such as enabling specific cluster features or defining the instance name and replica count, all from one location. Finally, the file templates/RabbitMQinstance.yaml serves as the payload. This represents your application's intent by defining the desired state of the RabbitMQ cluster. It is processed only after the operator dependency has been installed and has taught Kubernetes how to interpret the RabbitMQ cluster resource type. To expose the RabbitMQ management UI to external traffic, we utilize a Kubernetes ingress resource. A common challenge in this setup is service discovery. Specifically, the ingress must accurately reference the service generated by the RabbitMQ cluster operator. The key insight here is that the RabbitMQ operator automatically creates a service with the exact same name as your RabbitMQ cluster resource. In this architecture, because our resource is named Production Core, the corresponding service is also named Production Core. As shown in the traffic flow, a user accessing rabbitmq.example.com is first handled by the Nginx ingress controller. Based on the rules defined in our ingress resource, the traffic is routed to the Production Core service. Finally, the service directs the request to the backend pod, in this case, Production Core Server 0. This consistent naming strategy simplifies the integration between your ingress and the automatically managed RabbitMQ components. To implement the ingress in our Helm chart, we start by configuring the necessary parameters in the values.yaml file. This approach provides a clean and toggleable method to manage ingress configurations from a single location. As shown here, we define whether the ingress is enabled, specify the class name, and set the public-facing host URL. Next, we define the rule within the templates/ingress.yaml file. This template leverages the values we just configured to dynamically generate the Kubernetes resource. The ingress class name allows for flexibility, enabling us to switch between controllers like Nginx or Azure App Gateway with ease. We use Helm placeholders for the host and the service name. By relying on the RabbitMQ operator's predictable naming convention for the service name, we ensure traffic is routed accurately to the back end. Finally, we specify port 15672, which is the standard port for accessing the RabbitMQ management UI. To achieve maximum security within our cluster, we are moving from a traditional ingress model to an Istio service mesh. In the before architecture on the left, a standard Nginx ingress manages external traffic, but internal communication between services and pods often relies on unencrypted HTTP. This creates a vulnerability where the internal network is trusted implicitly once the perimeter is crossed. By transitioning to the Istio model, shown on the right, we implement a true zero-trust architecture. This setup enforces mutual TLS, or MTLS, for all traffic, covering both north-south entry points and east-west internal communications. As indicated by the lock icons, every connection is now encrypted and authenticated. The primary technical benefit here is that Istio's control plane, Istiod, acts as an automated certificate authority. It handles the complex task of issuing and rotating certificates for every service in the mesh every 24 hours, significantly hardening our security posture by ensuring that cryptographic identities are constantly refreshed. Enabling Istio and enforcing strict MET-TLS is a straightforward two-step process that builds the foundation for a secure, zero-trust network environment. In Step 1, we enable sidecar injection by adding a specific annotation to our RabbitMQ instance configuration. By setting sidecar.istio.io/inject to true within the metadata, we instruct Istio to automatically deploy an Envoy proxy container alongside every RabbitMQ POG. This proxy acts as a sidecar, intercepting all incoming and outgoing network traffic to manage and secure communications at the application level. Once the sidecars are deployed, we move to Step 2, enforcing strict mutual TLS. We do this by defining a peer authentication resource, as seen in the Istio mtls.yaml file. The critical component here is setting the MTLS mode to strict. This is the core of a zero-trust architecture, as it mandates that the system reject any non-MTLS traffic. This ensures that only authenticated and encrypted services can communicate with our RabbitMQ cluster, effectively protecting the data in transit from unauthorized access. In Istio, we separate the what from the how by defining the entry point through two distinct components, the gateway and the virtual service. Think of the gateway as the door that opens a specific port to the outside world, while the virtual service acts as the map that defines internal routing rules. On the left, we have the Istio gateway configuration. The selector binds this rule to the standard Istio ingress gateway controller. A key feature of this setup is the server configuration for port 443. We have enabled mutual TLS by setting the mode to mutual and specifying a credential name for the certificates. This is a critical security measure, as it requires the user's browser to present a valid client certificate before a connection can even be established. Once the traffic passes through the gateway, the virtual service on the right takes over. This map defines the host as rabbitmq.example.com and explicitly connects it back to the gateway we just defined. The HTTP route then specifies the destination, using a template variable to route traffic directly to the operator-generated service. This modular approach allows us to manage external access and internal routing logic as separate, clean configurations. This diagram illustrates a two-tiered MTLS security model designed to provide end-to-end encryption and mutual authentication for traffic reaching a RabbitMQ pod. In the first tier, which represents the external connection from the user to the Istio gateway, you are responsible for managing the certificates. This is handled via a Kubernetes secret named RabbitMQ admin certs. For this tier, users must provide a valid client certificate to their browser to successfully complete the MTLS handshake. Moving to the second tier, which covers internal traffic from the Istio gateway to the RabbitMQ pod, certificate management is fully automated by Istio through its Istiod component. In this internal environment, certificates are automatically issued and rotated every 24 hours, ensuring a high level of security with minimal manual overhead. By implementing this dual-layered approach, we maintain strict manual control over external access, while leveraging Istio's automation to secure internal service-to-service communication. The blueprint for production-grade stateful applications outlines 4 critical pillars for successfully managing complex workloads in a cloud-native environment. The first pillar is the foundation, embracing operators. By utilizing the operator pattern, we encapsulate operational domain knowledge and automate intricate lifecycle tasks. This transition from imperative scripts to a declarative state ensures greater stability and reliability. Second, we focus on architecture through packaging with wrapper charts. This approach involves deploying operators alongside their application instances as a unified package. Wrapper charts facilitate atomic, version-controlled, and repeatable deployments, significantly reducing configuration drift. The third pillar is accessibility, achieved through predictable ingress. We expose services via standard Kubernetes ingress, utilizing the consistent naming conventions inherent in the operator pattern. This simplifies service discovery and ensures external components can reliably connect to stateful services. Lastly, we address fortification by achieving zero trust with a service mesh. By layering a service mesh such as Istio over the environment, we enforce strict mutual TLS and automate certificate management. This final step secures internal communications and establishes a robust zero-trust security posture for the entire application stack. This pattern represents a reusable blueprint that provides a structured approach to managing complex services. It is defined by a 4-stage journey: foundation, architecture, accessibility, and fortification that serves as a maturity model for deploying stateful workloads on Kubernetes. In the first stage, foundation, we embrace operators. By moving from imperative scripts to a declarative state, we use the operator pattern to encapsulate domain knowledge and automate the intricate lifecycle management of our surfaces. Moving to the second stage, architecture, we package our components with wrapper charts. This allows us to deploy operators alongside their application instances in an atomic, version-controlled, and highly repeatable fashion. The third stage is accessibility, where we implement predictable ingress. By exposing services via standard Kubernetes ingress, we can leverage the predictable service discovery mechanisms inherent in the operator pattern. Finally, we reach fortification to achieve a zero-trust security posture. By layering on a service mesh like Istio, we enforce strict mutual TLS and automate certificate management across the infrastructure. While this model is demonstrated here, it is not unique to a single technology. This blueprint is designed to be applied to any complex stateful service on Kubernetes, ranging from databases like Postgres and Kafka to monitoring stacks like Prometheus.